This week 4, lesson 2, and we will be starting to learn new topic 4, but only the first part. Yeah, we will be having two parts, part 1 and part 2. So today we will touch on part 1, and I hope you have seen the lecture notes in PDF in files, class materials, topic 4, and chapter 4, part 1. Right? So without further ado, could you please switch on your camera and also microphone so that we can recite our dua. Ada masalah ke buka kamera? As soon as you enter the classroom at 10, you can already try your camera. You can switch on your camera. Maybe next time I don't need to ask. Does anyone have any problems since yesterday with the Windows 10 updates? Does anyone have that kind of problem yesterday?
No, still not updated yet.
No? Huh? You not, oh,
No
okay.
update.
Windows 10. Asal tak guna Windows 10?
Saya pakai tapi belum update yet.
Oh, belum eh? Oh, okay. Selalunya you punya update automatik dia tanya ke ataupun dia update je sendiri?
Saya block auto update sebab nanti takut laptop saya hang.
Betul. Sebab you block lah, you selamat. Saya tak block. Tak selamat. Yesterday was disaster. Until today, but it's still quite lagging and we are still figuring out why. Yeah, but you see dia punya nampaklah kelainan ni. But anyway, we'll start with our doa. We'll start with the doa.
Saya baca dua doktor.
Okay, terima kasih Kak Afsar.
Bismillahirrahmanirrahim. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Allahumma fil lana dzunubana wal walidina wa ma taqabbal saghira. Allahumma fil lana wal walidina warhamhuma kama rabbayana shaghira. Bismillahirrahmanirrahim. Allahumma ja'alni fi qabli
Qalbi nura wa fi
fi
lisani
lisani
nura
nura wa fi
wa fi
basari nura
basari nura wa
fi
fi
sam'i
sam'i nura wa an
ma'iyya
yamini nura
ma'iyya
wa an
sari
yasari nura wa min fawqi nura
wa min
wa min
tahti
tahti
nura
nura wa
min
min amami nura wa
wa
min
min
khalfi
khalfi
nura
nura
waj'alni fi
fi
nafsi
nafsi
nura
rabbi yassir
rabbi
li
shrah
salli sirri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli
li yafqahu qawli. اللهم
Allahumma
افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم
Arhamar
الراحمين.
Subhan rabbika rabbil izzati amma yasifun salamun alal mursalin walhamdulillahi rabbil alamin.
Amin, amin, ya Rabbal Alamin. If you have other dua that you want to add, Mr. Afsar, you can message me personally, then I can add in the PowerPoint slide. All right. Okay, so without further ado, we will start with our class topic 4. I will share my slide, then you can see top of your video. I hope you can see my PowerPoint slide already. Can you?
Yes.
Yeah. All right. Thank you so much. So we are, hold on. So this is lecture 4, lecture chapter 4. Hold on. I'm looking for my pen. And we will still be using the same textbook. And as you have seen last week, those are the few contents that we will be covering. And today we will cover a little bit until, yeah, only this, yeah, CR, and also a little bit on the mixed flow, yeah. So we'll see about that. But there are many other contents or subtopics that are to be covered in part 2. And you have seen this earlier as well, the summary or the overview of the whole thing of either liquid phase or the gas phase for that example of reaction. And we will also look into the isothermal and the pressure drop, by not considering the pressure drop in this topic as well, yeah, in chapter 4, topic 4. So, but that will not be covered today, and it will be covered in part 2. Okay, ideally, the batch reactor system will follow this basic formula based on the flows coming in minus the flows coming out plus the rate of generation of the species in the chemical reactor, which is in this case we use G to represent generated rate of species from the chemical reaction, which is equivalent to the rate of the accumulation, yeah, the rate of the accumulation of that species. So when we talk about the rate of accumulation, it refers to per unit time. So you have the change of the number of moles per unit time. Then the flow, you use the symbol of F. In, you would use the naught, and the J would refer to the species. Yeah, the out is simply what goes out. So if you have that, so we have FA naught, and coming out is FE. That is basic, yeah. But when we consider batch reactor system, so do not be confused. For us, we will take out a few things, which is there is no flow coming in and there is no flow coming out because we have a batch reactor system. Simply the chemical reactions in the reaction mixture in the reactor. So we have no flow coming in and no flow coming out for a batch reactor system. So therefore, those first two terms will be cancelled out. So it says that ideal batch reactor has no fluid enters or leaves the reaction mixture during the reaction. Now, so therefore, we only have the generation, generated species, which is equivalent to the rate of accumulation. Here, we want to see how we go about with the equation, yeah? So how do we write the generated, yeah, the rate of generation of J species? In this case, since we consider volume, so the volume is written as the sub-volume, which is the dV. In this case, first starts with the delta V1. So we have two sub-volume at different locations. So we have G1 that species A, which is depending on the rate of reaction of that particular species at that position times that subvolume. If you have different locations, so you use the same equation. Yeah. So if you were to talk about the GJ, the rate of the generated species is simply the summation of the subvolume equations. Yeah. So we have this summation of the rate of reaction and also the subvolumes. If we take, this is mathematics. Yeah. If we take it to infinity, then the subvolume will become not to say the sub volume becomes zero, yeah, but mathematically we say zero, then we can transfer or we can convert the sub volume symbol to delta V, yeah. This is what you use in your integration symbol, yeah. So we simply integrate for a specific volume having the rate of reaction of that particular species times the delta V, yeah. So that is why you have that in here, which is equivalent to the change of the number of moles per unit time. Now we have a consistent symbol used mathematically, which is the dV and also the dN. Now the question would be, how do we get the time? What time? How much time is needed to reduce the NA naught to NA1 or NB naught to NB1? All right, in this case, it means we know that, let's say, A plus B producing C plus D. So we want to know how much of this species A reduces. We know that through time, the C increases and the species C increases, species A increases. So how much time is needed to decrease or reduce that particular species as CA naught to CA new one, CA1, yeah, that can be another time. In this case, we can also refer to number of moles, yeah, the number of moles of the species A initial to number of moles of species A at the other time. Same goes to the other species, which is B. Yeah? So how do we do that? Knowing the equation that we have simplified, um, we are going to rearrange the equation and find T simply by, yeah, no, T is simply by integrating the other side. Yeah? So you bring that, the RA to right to the right and dt to the left and integrate the T, which is from T naught to another time T. And definitely this one will give T minus T naught. And T naught is normally 0. So what you get is T. Okay. And when you integrate both sides, so this is the outcome for the right hand side. Yeah? So you integrate the number of moles, the change of number of moles over RAV. Yeah. Since we assume that the condition is perfectly mixed, then we say the R is constant. So therefore, hold on. Yeah. So this is the first step. Yeah. After that step, you will integrate both sides, and in this case, we are saying we know that D and A over RAV, but now we want to integrate from a lower volume. Normally, the integration is that way, yeah? A lower volume to a higher volume. Volume means intensity, whatever intensity. Since we say that it is perfectly mixed, meaning in that batch reactor, any point in the reactor, the R is constant. So therefore, the R, we are not going to integrate the R, but we are going to integrate the number of moles because the number of mole changes through time. But for the batch reactor system, the volume is also constant. Yeah. So therefore, the R and also the V are constant. The only changing in a batch reactor system is the number of moles. So therefore, what we are integrating is the number of moles. normally for any integral initial and final, the initial is the lower uh, intensity. In this case, the lower number of mole. The top part is the higher number of mole, because you know, as when we have T naught, which is equals to 0 hour, then the NA naught would be the NA naught, and at that specific other time, let's say T1 at T hour, then we have NA. And we know in a batch reactor system, as T increases, the number of moles for that particular species would decrease or increase. For that particular species, the A is now the reactant, so decreases. Yeah, so that is why the lower integral point is the NA1. Yeah, in this case, we have NA1. So NA1 is lower than the NA naught. Right? So that is why it starts with the NA1 to NA naught. But then we, okay. All right. Okay, that would be okay. I want to explain to you why we have the negative part. So I have to write it here, yeah? So normally when we have this DNA over FRAB. So now the question is why it suddenly becomes negative. So normally kita akan start dengan T equals to 0 lah katakan lah, and then T. And that T equals to 0 is NA naught. And T is NA. But that is illogical, yeah? Then because of that, we have to switch. Because the NA here is lesser. NA naught here is bigger. So the bigger should go up, the lesser good should go down. So that is why we put negative sign there. Do you have any question? Mathematics lah. When we deal with equations, then we should make sure that we understand the mathematics principle or basic theories as well. Right? Do you have any questions before I proceed? No.
No.
Huh? No. Okay, thank you. No so far, yeah. But you can stop me anytime, yeah. Now, this is what you have seen earlier, and now we after the integration, we can find the time needed to reduce from one number of mole to the other number of mole, yeah, at different time. We can also write we can also find the time needed to change the number of moles based on the information of the change of the conversion. So we can use this formula, and where does this formula comes from? So it comes from the previous slide, whereby this is from previous slide. Yeah, you see that in week 1, right? We know that the NA naught times the change of conversion per unit time is also equivalent to minus RAV. Okay, so by using that equation, we can find the time. Yeah, simply rearrange that equation. Yeah, you have that equation, and we know that the NA naught, the assumption used, is constant because, of course, initially the number of moles for the species initially is considered to be constant, yeah, a specific value. So you don't need to integrate the number of moles initial. Take it out from the integral part. So you only integrate based on the change of the conversion, right? So we can use also this formula to find the number of moles at the change of number of moles for a specific time by also using the change of the x. All right. So we know that in a batch reactor system, as T increases, the number of moles of the, let's say, the reactant A would decrease. And as T increases, the X of the species would increase or decrease. Increase or decrease? Increase. Tak dengar suara ke? Ataupun tak ada siapa jawab? Kalau tak ada siapa, kalau tak nak buka mic, you can type in your chat box, yeah? Alright? So I don't need to wait. So you can type in. Ataupun komputer awak pun lagging hari ni. Komputer saya lagging tak hari ni? Bila saya tulis, dia lambat keluar dah.
Ada okey je, okey.
Okay, Alhamdulillah. So, thank you. So we have two formulas to find how much time is needed to reduce the number of moles, yeah? The first formula is based on the change of number of moles, yeah, this one. And the second formula is by the change of the conversion. Yeah? Right. Now we are going to consider the number of the how much time needed for a first order reaction. Yeah. So for first order reaction, 1 mole of reactant produces 1 mole of product. So we know that, oh, ini subscript, yeah, subscript. So do not get confused. This is also subscript. Masa saya betulkan tu, I forgot to change, yeah. Right. So minus RA, the rate of reaction of the species A, which is the limiting reactor. In this case, we assume K A to the power of 1. So that is first order, yeah, because we say that it's elemental, it follows the stoichiometric, yeah. And we know that the change of number of moles is equivalent to RA times V, right? So we are going to use the assumption to rewrite this equation so that we can find the how much time needed for a first order reaction situation. Yeah. So the first thing that we can do is to substitute the formula of Na. Knowing Na, yeah, the number of moles at that specific time is equivalent to the initial number of moles minus the consumed, yeah, number of moles. So that would be the formula that we will substitute and put it in the Na, right? By using A3 means assumption number 3. Divides by dt and equivalent to minus. Of course, the RA is simply following, since we are assuming for first order reaction. So the minus the RA is KCA. So the minus RA is KCA. The RA is simply minus KCA. So that is why you have this minus KCA times volume, right? So once you have d over dt, so whatever d to the constant volume is considered 0. So you have that 0 minus Na is considered to be constant. Yeah, I don't put there here. So Na naught, yeah, is considered to be constant. So you don't need to differentiate this one. Then the only thing that you differentiate is the change of conversion. Yeah? So dx. So minus Na naught dx. Then dt, we bring it there to the right hand side with the k. And we know by using assumption number 1, where is assumption number 2? Supposedly assumption number 2, yeah? Ca is equivalent to Na over V, or Cav is equivalent to Na. Yeah? So since we have Cav, then it's Na, so you bring it there. Yeah? Meaning you are bringing all the N entities together at one side, to the left-hand side. Now, you can simply, again, substitute the Na, because we know that the Na is Na naught minus Na naught x. So you can now cancel Na naught. And what is left is the dx over 1 minus x, which is equivalent to minus k dt. Since we want to know time, so we are going to integrate that, and k is constant, so you don't integrate constant, yeah, you take it out from the integral symbol. So simply bring it to the other side. So 1 over k, then we have the integral of the time t naught to t. Then of course, we have x naught to x, yeah, 1 minus 1 minus x. Here, since we have negative, so both are cancelled out already. So now it becomes positive. We don't have negative symbol already, yeah, anymore. Simply simplify the integral of 1 over 1 minus x dx, and that would be the outcome for that integral, yeah, which is ln of 1 over 1 minus x, right? So you have 1 over k, then ln 1 over 1 minus x times t. Here it's simply t minus t naught. And we know t naught is 0, then what is left is dt. Okay? So that would be the equation for a first order reaction. When you have first order reaction following that formula or equation, reaction equation. Do you have any question before I proceed?
No, doctor.
No.
All right. Very good, Karia. Asar, thank you. Now we are going to go to the next slide. Hmm. Again, you see the derivation. Yeah, why I like to show the derivation, because engineers, if they are given a situation, you don't know the formulas, then you start with integrating or differentiating. But of course, in the real life, you can simply refer to the formulas as long as you understand the theories. But here, since you are undergrad students, you cannot simply memorize without understanding the basic theories. It's very crucial that you understand where this equation comes from. So this is what we are doing, yeah. So for a first order reaction, but we are going to assume uh, for a batch reactor system, yeah, having this is the batch reactor system. I'm going to change the color of my pen because I used red already. Hold on, I'm going to use blue. Okay. So that would be your batch reactor system. You know that in your batch reactor system, we have a specific volume, we have rate constant, we have conversion. I think this is volume. This is uh, the volumetric flow rate. If we are dealing generally, yeah, when we say that in a reactor system, if we have flow in, then flow out. But of course, you simplify that when you say it's a batch reactor system, you simply cancel that out. Then when you don't have the flow, then you don't have the volumetric flow rate. Yeah? The only thing that you have, of course, the volume. Yeah. Then we have the number of change, the change of moles, yeah, and A naught to an A, then the change of the concentration. So from your basic equation, since there is batch, so you don't consider that. And for the generated species, when you, this is what you have done earlier, which is equivalent to the RA times V, dNA over dt. This is what you do to replace the Na, assuming the Na is equivalent to the initial minus consumed. Then we have first order reaction. We arrange that again, yeah. Then substitute the equation of DNA, cancel that out, and finally, this is what you see, yeah. So the same thing that you see from the previous slide, right? But here I make it much clearer with the assumption used for a basic reactor. Yeah, you have a pipe, you have a pipe in and pipe out just to flow your reaction mixture. But when you decide to make it batch, then of course there is no continuous flow. Yeah, for that stream in and stream out. But you still have the pipe there. Yeah? If not, how are you going to put your reaction mixture in the reactor, right? So this is how you simplify things with your basic understanding. Of course, the assumption that you use is for a perfectly mixed reaction. There is no variation on R everywhere, yeah, in the reactor system, and there is no change of volume, yeah, because you assume it's a batch reactor system, constant volume. Okay, right. We'll go to the next one. Ya, saya tengah cari mouse saya. Mouse saya hilang. Ah, dia lagging, dia baru keluar. Masih hilang. Ah, okay. Right, this is the same thing. Saya lupa delete lah kot. Alright, so we'll go to the other slide, slide 14. Now we are going to see how we find how much time needed for a first order reaction, whereby the time needed change the number of moles of that reactants based on the function of C. Yeah. So how do we get this equation? Yeah. You don't simply memorize this. From this equation, the reaction time, we know that it depends on the concentration of that species and also the initial concentration and the rate constant. How do we get this equation? Yeah, it starts with the basic equation for a batch reactor system, which is dNA over dt, the change of number of moles, depends on the rate of reaction times the volume, right? Now, since we know that the number of moles is equivalent to concentration times volume, so you are going to replace that here, right? First, kita tolong betulkan, so there is subscript, yeah? Got to change that. And then you see that on both sides, left and right, we have C there and we have C there. So we are going to gather the concentration symbol together. Yeah. Now, what you want to find is time. So you're gonna bring the time to one side so that you can integrate that, which you do here, and gather all the other symbols at one side. Yeah. So we have that equation, and we know that the volume is constant, so you are not going to differentiate the volume. So you take out the volume from the differentiation, yeah, dCA. Only you differentiate the change of concentration, right? Since we have V there, of course, then you can cancel out V, and the K is constant. Again, if you want to find the time on the right hand side, you integrate, then you of course integrate on the left hand side as well. Since the rate constant is constant, so you take it out from the integral, so you don't need to differentiate the rate constant. So what you do now is you integrate from the initial concentration of A to the final concentration of A. All right, so we have basically, this is written this way, yeah? 1 over CA dCA. So you are integrating 1 over CA, right? CA naught to CA. This is how it looks like. So the final equation based on this integration is the ln of CA over C naught. Basically, this will give you ln CA. And since we integrate from CA naught to CA, then of course it becomes ln CA minus ln CA naught. Okay, so that is simplified as ln CA over CA naught. So those are simply mathematics, yeah. So if you forget what you have done so far from your calculus, so I try to show my best so that you can remember back your calculus integration and differentiation part, right? So that would be your equation for a first order reaction on how much time needed for the change of number of moles or the change of concentration for a specific reactant. In this case, A, reactant A. Okay, so we are now going to do the same thing for the second order reaction. So what is second order reaction? So when you say second order reaction, if you look at the assumption number 4 here, it's a second order reaction. We know that the rate of reaction for species A, which is in this case minus because the rate of disappearance of A, the reactant A, is equivalent to the KCA squared. Yeah, of course, you start with the basic equation. It's a batch reactor system, so you cancel out the flow. Then that will be a basic equation. Here, you replace the NA by using assumption number 3. And then we want to find the time. So put the time on one side and the rest would be in the other side. Then, of course, here we got 0. What is left is minus NA naught dx, yeah, because D, so you differentiate dx. Then replace RA, which is now, RA is now minus K here, minus KCA squared. Then we say that since the batch, there is no change of volume, so dV equals to 0 or V equals to V naught. Yeah, the volume is constant, so therefore we can simply replace the V to V naught, right? So we have NA naught, then CA, and then V naught here. Now, we know, since we know we have V naught there, so we are going to simplify things by introducing the NA naught is actually is CA naught V naught, so that we can cancel out the V naught. Yeah. So we have CA naught V naught here. Earlier we have CA naught V naught. So that is why you can cancel that out. Yeah. Right. So we have CA naught over A, of course, here negative becomes positive. KCA, all right, CA here. We are going to apply this assumption number 6, yeah, whereby it says since the volume is constant, so this is what you have done so far from last week, yeah. For a constant volume in a batch reactor system, we know that CA is depending on the initial concentration of A, open parenthesis 1 minus X. So that is why we have there, yeah, CA to here, right? Since CA is squared, then the whole thing you write twice. Yeah? CA naught 1 minus X, CA naught 1 minus X. So cancel out the CA naught. What is left is, of course, we have the dx. The conversion is changing, so you only integrate the changing parameters. Yeah, in this case, we have since 1 minus x twice, then 1 over 1 minus x twice. CA naught is constant, so you don't integrate constant. So you take it out from the integral part. So the only thing that you integrate is 1 over 1 minus x squared, right? From initial x to final x, which is x naught. In this case, x naught, as you start t equals to 0, the x naught is 0. As t equals to t, of course, the x increases, right? So you integrate from 0 to x, okay? So the outcome for that integration is x over 1 minus x, right? So the outcome for 1 minus 1 minus x squared dx is x over 1 minus x. Right? So that's why you have that. Then those are the constants. So finally, the time needed for a second order reaction depends on the conversion for CA naught and the rate constant based on that formula. So we go back to our previous slide for a first order reaction. Yeah, how does the T looks like? Yeah, so the T for the first order reaction is depending on the Ca and Ca naught ln and times one the reciprocal of the rate constant. But for the second order, we have x 1 minus x, then Ca naught, and also the K. Right? Okay. Now, why the K is considered constant here? Because the K can also change based on the change of temperature. In this case, if you assume isothermal condition, so the K is considered constant, right? Then the concentration of the reactant A at initial time is also considered constant. So those assumptions 7 and 8 is useful for you to decide whether you need to integrate this inside the integral part or not. If they are constant, then you don't need to integrate it, right? Okay, do you have any question before we proceed?
No.
No,
No,
doctor.
thank you, Afsar. Yeah, thank you, Karya. All right, now we are going to look at this table 4.2, batch reaction times, meaning the question would be, which one would need more time? Is it the first order or the second order? So you see the summarized formula for the time needed, yeah, right? So if you look back at our previous slide for the second order, the time needed is that one. So here is the second order. And the other formula is for the first order. And the table 4.2 gives you based on hours, minutes, seconds, or milliseconds. Yeah. My question would be, which one will need more time? Is it first order or second order?
Second.
Yes, second order will be needing more time. Yeah. If you look, if you flip from your Fogler chapter 4, so please also see the examples on how we start to calculate how much time needed if it's first order, and now how much time needed if it's second order. With the condition, we need to know the rate constant. Yeah. So the question would be, how would you know the rate constant? So normally, if you want to know the rate constant of a specific reaction, then you have to do some experiments, and the K can be decided from experiments. Remember last week we did on the linear line graphical method to find the K. So that would be the way on how to determine the value of K by collecting data. Yeah. So if you cannot remember still, then you have to flip back your week 3 lecture notes, yeah, in topic 3, yeah, how we determine the K. And I did give you the assignment, which is due tonight, 11:59. You group K kan? JK, betul lah, tonight, betul tak? 11:59. One of the is the question is to determine the K.
Bukan semalam ke? Malam
Ha?
semalam.
Semalam
Ah,
bukan hari ni. Alhamdulillah. Okay, dah hantarlah semua.
Tak.
Yeah, I yesterday I took my time to actually look those people who submitted your assignment masa kelas hari Isnin for the SOP assignment, and at that time ada orang yang tak hantar lagi, and for your information, the assignment can be sent late. I can see it's a late submission. Yeah, so what I want you to do is, don't be scared if you find it hard to understand and take longer time to submit it. What I want you to not to copy other people but try on your own. If you submit lewat, then you have to tell me lah kenapa submit lewat, right? Maybe you tak faham ke apa ke, that's why you submit lewat daripada you tak submit langsung. So at that time, there are still few people who did not submit. So please try to submit at least, please. That is your practice, right? Now, the next slide is before we take our break, then we will first go through another 2 slides showing you a typical orientation that you have to understand when you want to set up your reactor, right? Now, of course, in this class, you learn on the theories, you learn formulas, you see mathematical formulas everywhere, integration, differentiation, uh, you rasa penat. But it will become easy along the way as you practice through time. But of course, it does not mean that you belajar teori je, you tak nampak practical. Okay, so this is one of the example that you know what to expect when you want to set up your reactor. When you want to start your reactor, of course, you have to prepare your reactor. Is it for batch or is it for not batch? Right? So we have activities in setting up your reactor. So those are the few activities. Yeah, the first one, and that each of the activities needs time, right? So this is the examples of time needed for each of the activities. For example, TF, which is to feed the reaction mixture in the reactor and starting to agitate the reaction mixture, meaning that is your reaction mixture. Berapa lama time needed to fill in the reaction mixture? Yeah, so it is recommended to be normally, commonly, half hour to 1 hour, depending on the size. Then you ask a question whether your reaction is isothermal or non-isothermal. So if it's at that specific temperature, then you have to heat the reaction mixture to a specific temperature. Yeah. So it may take another half hour to 2 hours. Then only you can start to run your experiment. Yeah. And the the reaction mix time varies based on your target for X, right? So the time varies when you carry out your reaction. And once the reaction ends, through time, you may take the sample and check, oh, dah achieve ke conversion yang you nak tadi? So you may stop the experiment when your target is achieved. Then you will go to the next step, stop the experiment, and before you empty, of course, the process of emptying and cleaning the reactor. Of course, emptying, you have to take out here and do the separation. Ya, dia akan pergi separation lah. This class kita tak tunjuk lah separation tu, kita cover reaction saja. But of course, you have separation class in this semester. Yeah, so you will go to separation because what you want, let's say A plus B produces C plus D. What you want is only the main product, but you don't want the D, let's say. Or you still want the D, but you want to sell it separately, the C and D. Who wants to buy a mixture? No one. People wants to buy the pure product. Yeah, so you have to separate it. That is the other class that you learn this semester. Because you need another time to clean and empty the tank, the reactor, and the total time excluding the reaction. Yeah, let's say 2, 1, 2, 3, 3, 6. Here 0.5 plus 0.5 plus 1.5. So 1, 2.5, excluding the reaction. Only to prepare, prepare before the reaction starts and also to prepare for the next reaction. So you have to clean it. Yeah. So the total time is from 2.5 to 6 hours. So these are the things that you have to consider when you do your plan design in part 7 and part 8 in your final year. Students sometimes they forget, they only think the reaction dah habis dah. Dia tak ingat apa dia nak kena prepare, dia nak kena re-prepare for the next step. So you will learn that in your plan design scheduling. Yeah, I hope it is taught clearly when you reach your part 5 semester. Yeah, scheduling, how to schedule your process, not only the reaction process time, but also the preparation time. Okay, all right. So the last slide before we take our 5 minutes break. This table shows you the summary of the batch reactor system for irreversible reaction. Of course, here we only use a simple reaction equation here. A produces B, and we are assuming isothermal. And of course, when we have batch, then it's the same volume. Yeah, V equals to V naught. The mole balance, this is what you wrote from the mole balance equation. And you have two equations for first order and second order, which you have learned earlier in week 1 till 3. For a constant volume, you can rewrite the equation. For a constant volume, you know the CA is equivalent to the CA naught, open parenthesis 1 minus X, close parenthesis. So this is what you learned so far from previous weeks. Then when we rewrite our equation from the mole balance, this is our summarized equation for the time needed, yeah, for a first order reaction and the second order reaction. Okay, so we will take our first 5 minutes break. All right, thank you. We'll see you again in 5 minutes.
Okay, doctor.
Okay, doktor.
Welcome. Okay, so we are back for our second part of the part one, right? So I'm gonna share again my slide. Can you see the slide now?
Yes.
All right. So something happened just now. I closed it, then all my writings just now just lost. But anyway, it's okay. It's recorded. Yeah? And I hope you also have your own scribbling on your own notes. So we are going to proceed with the next one. Before we proceed with that, so we are refreshing of what we have done so far. That would be the reaction mixture, the reaction time needed. Yeah, I'm going to change my color of my pen to blue. Sorry, my computer is a little bit lagging today. So that is the basic equation for time needed for the change of number of moles. And now we are looking into what it means to have those formulas, right? Let us start with the first box here. We know this is what we found. We have the basic equation, knowing that basic equation, which is the change of time is equivalent to the change of number of moles per RAV. Yeah. If we were to integrate, so we want to find the time, so we integrate both sides. So what does it mean by the integration? So what you are integrating is the area under the curve. Yeah, what curve? So when you have this formula whereby you have 1 over minus RA times V. I'm going to change, sorry, I forgot to change my face. Now it's better. You can see me, right? So simply when you plot 1 minus 1 over minus RAV versus the change of dx here, which is dx, which is the x, then when you start to integrate it, it means the area under the curve, yeah, from x equals to 0 to another specific x, which is xa. So the whole thing is area under the curve. The curve means the integration part, yeah. So and it is known to be t over an a. So the area under the curve means t, the time over an a naught. Right? This is mathematics. This is simply refreshing of what you have learned in your calculus. But if you find it new, then good that you know at least before you graduate. All right. Now, the same thing goes to when we have that equation. Yeah. So if you plot 1 over minus RA uh, versus the change of x, the change of conversion from 0 to specific x. So that curve would give you the area under the curve from 0 to xa is simply t minus over ca naught, right? Area means t over ca naught. Okay, the same thing here. And that expression can also be re-expressed rather than in terms of x conversion. Now we change it to in terms of concentration, right? So the change of the y-axis 1 over minus RA versus the change of the concentration from a specific CA naught to CA. Of course, your CA naught is your maximum, yeah, maximum. And CA is your minimum because as time increases, the CA decreases, assuming the A is the reactant. Yeah? In this case, we have a decreasing trend, yeah, because we are looking into the change of the concentration of the reactant. So it is a decreasing trend. But for the X, of course, as time increases, the x increases. So ascending trend, right? Therefore, the area under the curve from initial to final will give you t. Okay? All right. So that would be the meaning of the integration that you do from your basic equation. Now we are going to go to a mixed flow reactors. Yes, yeah, mixed flow whereby you have flow in and flow out. So this is from your previous slide last week, week 3. We learned about the flow reactor system where you have the feed rate entering and leaving. So this is how it looks like. You have the feed in and the feed out. And you know that the volume in the flow reactor system is simply the change of the flow in minus out over the rate of disappearance of that particular species. You also write based on your basic equation, basic mole balance equation. And finally, you reach to a final equation for a flow reactor system with certain assumptions, and you have come up with a specific formula for the volume. Yeah, this is what you did last week, right? I'm just showing through what we have done so far, but if you don't remember, please go back and relearn, right? So the volume for a flow reactor system, the volume is simply the FA naught minus the FA over the rate of disappearance. Now, we can also find the volume from your previous slide based on simply substitute the flow, which is equivalent to concentration times this time volumetric flow rate. The epsilon is the volumetric flow rate. Remember, for a batch system, we have NA, which is C times V, right? But for a flow reactor system, we have FA, which is C times the volumetric flow rate. Okay, so please remember that. Huh? So we are replacing those. So if it's FA naught, then CA naught, and the volumetric flow rate initial. If it's final, then of course the volumetric flow rate final. Okay, that would be the equation that you use for the flow reactor system. Now, this week, since we are looking into the same flow reactor system, whereby we have the flow in and flow out, so we write the equation. And if there is no phase change, that is also what you learned last week. If there is no phase change, no volume change, then you can assume the subscript, yeah, subscript 3, right? Volumetric flow rate is equivalent to the initial volumetric flow rate. So that is valid when there is no phase change and no volume change. Yeah. Therefore, when this is constant, since it is still flow reactor system, so instead of using C, then we use F. FA is equivalent to the initial flow rate of the A, open parenthesis 1 minus X, close parenthesis. The same thing like when you have a batch, when you say V is equals to V naught, then the CA is CA naught 1 minus X. The same thing, yeah? So that is batch. But here we are saying that there is flow. So you use the same concept but using the F. All right? So therefore, you are going to substitute the F in here, having the conversion factor in the volume. All right? So the volume for the flow reactor system can be found when you know the conversion and the initial flow rate of that species. All right? Divides by the rate of disappearance of the same particular species. Okay? So this is for flow reactor system. This is again from our previous slide showing what we have done so far. Of course, this is for batch, then you use CA. When you deal with the F, then you use the F. Then, of course, those are the equation when you substitute the volume to the volumetric flow rate for a flow phase. Right? And now, since we know that here, That is your first equation, yeah, for volume in a flow reactor system, knowing the initial flow rate and the conversion. We can also find the volume for a flow reactor system by also using other than the conversion, but now we can use the C and also the volumetric flow rate. So where does this comes from, right? Where does this comes from? Um, Note that from our previous slide, if I go back, okay, we can write the volume for a flow reactor system in the function of the volumetric flow rate and the C's. So we start from there here, right? And simply simplify the equation. We have this initial volumetric flow rate and final volumetric flow rate. When we are dealing with the liquid phase and when the volume stays the same or the volumetric flow rate stays the same, yeah. So those are the things that you can assume, yeah, when you have a liquid phase, there is no change of phase. So we can say the final volumetric flow rate is equivalent to the initial volumetric flow rate, right? Meaning, apa maksud? You have this reactor flow in, flow out, yeah. Flow in is FA naught, then flow out is FA. Then of course, when it comes in through the pipeline, dia mestilah at certain velocity, yeah, velocity of the mixture. When it is liquid, there is no phase change. Apa dia masuk? We can say the epsilon naught is equivalent to the epsilon. Dia masuk, dia react, so dia keluar. So the velocity, the volumetric flow rate are the same. So this is what we are doing, yeah. So we substitute this to the initial volumetric flow rate. Simplify that, so you finally can find the volume of the flow reactor system if you know the volumetric flow rate initial. And of course, you know the CA naught and at which X that you want to target. Meaning, how much is the volume needed when you want to target for a specific conversion, for example. Yeah? Depending also on the rate of disappearance of the reactants and the concentration initial of that species. Okay. Next, so those are basics. Now we are going to be more specific, whereby we are going to look into first order reaction. We have the reaction as basic, so those are the formulas, this slide and also the previous slide, how to find the volume. But what happens if it is first order? So how do we start? Of course, you start with your assumption. And when you are dealing with liquid form, no phase change, then you can say that the initial volumetric flow rate is equivalent to the volumetric flow rate is equivalent to the initial. And if it's first order, then you write the rate of disappearance equation. First order. So you start with the equation that you generate earlier from basic understanding. Then, since we use that assumption, if we are referring to the concentration of A, puasa, tak boleh minum. Tekak kering. Sekejap, kena basahkan air liur. Yeah, so you substitute that into this equation, yeah, when we have DCA there, simplify it by cancelling the same symbol, and the volume for the first order reaction is simply the initial volumetric flow rate times X over the rate constant, open parenthesis, 1 minus X, close parenthesis. Now, we also want to find the tau. Tau means the space-time. Space-time is simply the volume of the reaction mixture divided by the volumetric flow rate. Yeah. So we have we simply substitute the V there for first order in there, in here, then simplify it. So the tau, which is the space-time, is simply X over the k times open parenthesis 1 minus x close parenthesis. Okay, so if you want to know the space-time, then simply by knowing the x and the rate constant, you can find the space-time. Yeah, other than knowing the volume and also the volumetric flow rate. So you have two formulas there. Yeah, so whichever formula that you have, so you can find the space-time. Now, when we do our reaction, you may start with a small scale, then you want to upscale it. Yeah, meaning we can resize the volume of the flow reactor system. But then, how do we resize it to at which volume for a specific conversion? Yeah, for the same conversion in a bigger scale, what would be the volume? We can use Levenspiel plot. It's a method application of design equation. Again, our assumption, we stick to the same assumption. For this case, starting, yeah, when there is no phase change, no volume change, the volumetric flow rate initial is constant. Yeah, and if we do that for a first order reaction, so simply substitute that, and we are going to use the graphical method where you have this rate of disappearance to predict the volume, yeah, the resizing volume. So let us go to the next slide. Now, knowing this equation simply by plotting 1 over minus RA versus the x, the change of x, then you get this plot. Now we'll give you a plot. Then, right? Uh, then you how do you get this plot? Yeah, it comes from the experimental data, which is the raw data, right? So at specific x, you take sample, then you calculate the x, the conversion, and the rate of reaction or the rate of disappearance of the species A. Then you can also, since we know this, if you were to plot FA naught over RA versus the x, you get the same trend. Yeah? So meaning here, the volume of the reactor varies with the reciprocal of DRA, right? Knowing certain, of course, this one means here, knowing certain flow rate entering the reactor, the plot of that, yeah, this one, okay, versus the change of the conversion can be plotted to determine the size of the reactor, both the CSR and PFR. Yeah, having the flow in and flow out, and also the plug flow reactor. So if you don't remember what plug flow reactor, so just refreshing, uh, plug flow reactor is like a long column, so masuk keluar macam tu je. So reaction dalam ni. So it can be a whole stretch of the reactor in a pipe, right? CSTR is like that, right? So you have flow in, you have flow out. Right? To do sizing of a CSTR is simply by determining the volume exiting at specific x achieved at the outlet of the CSR. So to find the volume of that specific system, simply you find the volume at the exit of D. Meaning, kata dia one whole stretch kan, dia masuk FA, keluar FA not there, keluar FA. Then of course, the volume for the whole stretch can be found at the exit. Alright? So this is what it is. So the design equation now based on the basic equation of the CSER, you can also use a Levenspiel plot whereby you plot minus 1 over RA versus dx, right? And it will give you the V over FA for the area under the curve, right? Okay. Here is simply how we rearrange the equation to find the tau, which is the space-time. So let us go back to our previous slide about the space-time. Okay. So this is the space-time that we have tried earlier for a first order reaction. Yeah, which is the x over k 1 minus x. First order reaction, tau, which is the space-time. Go forward, right? Here, we are not yet into first order, second order, but generally by using the Lebensspiel, you plot your data, then you know just simply rearrange. The volume can be written as such, having a factor of concentration and volumetric flow rate, not only the flow rate initial, but also their expression. Yeah. So from here, uh, if you from here we can also find tau, since we know tau is volume over volumetric flow rate initial. Simply rearrange that, then we get that equation, right? And we know that the V over FA naught is equivalent to X over minus RA exit, which you write earlier. Yeah, meaning tadi understanding kita tahu the volume of a specific reactor system depends on the exit. Yeah, so here simply means V over FA naught, then we have CA naught. So that would be the general equation, design equation for a space time for a CSTR. Okay, so kita advanced sikit. Now we are entering the plug flow reactor. So this is what you have learned earlier yang saya scribble tadi. So there is a plug flow reactor coming in, coming out, right? And those are the equations just to refresh you back. In the plug flow reactor, the rate of reaction depends on the change of the flow rate because masuk, yeah, flow rate, initial and final. And also the volume. Remember, volume berubah, ya. From volume, volume increasing. If you go to your right, yeah. So volume, this one is volume plus delta V. Here, volume plus delta V plus delta V, yeah, something like that, yeah. So this is what you see earlier, okay. Then you also find the volume. I just take it from your textbook based on the integration, knowing that your initial flow rate is constant, right? Then you also write this formula for the molar flow rate at fat at that particular time is equivalent to the molar flow rate initial open parenthesis 1 minus x close parenthesis. And you also use this correlation for the flow reactor system using the ideal gas law, right? Just remember that we keep using this formula in this week as well, especially the formula of the flow rate, yeah, which is C times the volumetric flow rate. Okay, please remember that as well. That's basic. We know this as well. We did the stoichiometric for the flow reactor system with all the F. All right. Now, so this is what you learned this week. Yeah. So having known that uh, as you go to your right, the volume increases, yeah, or changing. But of course, when we want to write a specific formula, we always take a control volume, a small control volume, where there is no spatial variation of R. Meaning at 1 point, of course, the R is constant. Yeah, but of course, if you go to your right, from 1 point to the other point, the rate of reaction varies. So we have this equation, the FA naught at V minus going out, FA naught at V plus delta V. Then generated RADV, of course, with the assumption there is no variation of R, so you don't need to integrate the R, only the delta V, yeah, the subvolume. And if you assume steady state, it is not written there. I hope it's written somewhere. It is not. Then this is considered zero, yeah. So simply rearrange that. So this is mathematics, yeah. Since we have the subvolume, but when we want to do the integration, we cannot integrate the subvolume, yeah. So we have to write it in terms of dv, yeah, delta V, or delta V, whatever, mathematically. So ini masih belajar calculus, tak tahulah calculus 1, 2, 3 ke. So if we want to convert this subvolume to dV, then of course you take a limit, the delta V goes to 0, then of course the subvolume, the delta V here becomes the delta V for the integration. Then only you can start integrating. Okay. So therefore, for the flow reactor system, this is the formula. The rate of reaction depends on the change of the flow rate and also the change of. So that will be the summary of the design reactor. We have CSTR, which is that volume. Then for PFR, the change of the flow rate and volume is equivalent to the rate of reaction. Integrating it, then you get the volume. So this is packed bag. Yeah, this one P is packed, B is bed. So you have the column, you have the bed, the beds of packing. Yeah, those are packing. Right. So you will learn that later, not now. So that will be the end of the week 4 punya part 1 lesson. All right. Uh, I simply make it slowly because I want you to get familiarized back to the integration and differentiation because that is theories, right? It's very important. So for the rest of the 20 minutes at least, we will go to our breakout room, but I will share one simple exercise for you, right? So I'm going to stop sharing this and reshare the exercise. Then only I will let you be in your own group if you read from the agenda to solve that simple exercise. Okay? Hold on a second. Habis tu kita buka lagu dulu. Relax, relax. All right. So can you now see the PDF screen? I have also uploaded the PDF in your chat box. Can you now see it? Can you now see exercise number 1, topic 4?
Yes.
Right. And if you want to take the copy, then you can download the PDF from your chat box. Yeah. Exercise 1, topic 4. So let us read the question. Consider this elementary equation. Oh, lupa. Sekejap na. This is not PowerPoint. I am going to use comment here. The tukar color. What color do you want? Green, blue? Green lah. Alright. So we are assuming it's an elementary equation. So therefore, 1 mole of reactant producing 1 mole of product. So the rate of disappearance of that particular species A, in this case, follows the stoichiometric, then it is considered to be a first order reaction. So the reaction process was carried out in a constant volume, yeah. So that is already your hint, yeah, constant volume in a reactor, whereby the volume is equivalent to the initial volume. And the volume given is 200 meter cube. Imagine how big is that? 200 meter cube. 1 meter cube is 1000 liter. All right. So if it's 200 meter cube, then it is how much? 200,000 liter. Can you imagine how big that is? Very big. So now the question gives you the K value is 0.12 per unit time. In this case, minute, per unit minute. So we got 2 questions. Now, how is the rate equation written? Write down the rate equation for the above reactions. That is one. Rate equation. Secondly, calculate the time necessary. So you need to find the time. Meaning, in this case, if it's first order, then the time for the first order condition. To reduce the moles of A in the batch reactor system, achieving 99% conversion. Right? So I am going to divide you into groups. Very simple one. You can refer to your lecture notes and show the steps how you get to your equation. What is the equation used for time needed? Yeah, time necessary needed to reduce the number of moles reaching 99% of conversion. Right? Do that in your own small group. Can use Microsoft Whiteboard ataupun discuss sama-sama dan finally show the outcome of your discussion. Yeah, I'm going to divide you into groups. Do you have any question before that?
No, doctor.
Very good. So how many people we have today? 25, excluding me. So 8 groups, 3 people in a group, yeah? Right. Getting ready. We are creating your rooms now. Microsoft Teams says. We are creating your rooms. Then I'm going to click start rooms. Then get ready. You will be headed to your own group. Sorry, lamanya. Siapa pun masuk group lagi? Tahun ni masalah laptop saya ke? Masalah apa? I think my laptop lah since I told you since yesterday. Saya kena tukar dia punya. Sudah open? Saya cakap seorang-seorang.